Right, so today is April 21st. (2021). So let's just go over some things that are due. One of the things that is due is homework 18, so turn that in next Monday for 10 points. I changed the test date, so your test 4 is next Wednesday. Okay, and next Wednesday, I believe, is the 28th. And quiz 4 is also due next Wednesday, so upload that to Canvas. That is also the 28th. Now, if you did good on all 3 of your quizzes and don't feel like turning it in, that's also fine, because I dropped one of the quizzes. So lab reports. There's one on spontaneity. And then there's this one's kind of late, but your acid-base problem set. So make sure you turn those in. For those of you that have come to lab, if you turn in your lab notebook, it's very important you maintain a lab notebook if you really want to work in a lab or go into science. So if you turn in that lab notebook, I'll give you 100 points. So that's going to be due next Monday, because next week is our final week. In fact, next Wednesday is the last time we'll meet to get. Yeah, that's the last time we will meet. So that is 4/26. And if you're doing the clutch prep drills, make sure you continue to do that. I got an email from the representative, so I guess she wants to talk to me, and she also wants to know how you guys did, whether you like the service or dislike the service, and give them their feedback. And I believe you get $50, or you're in a raffle for a $50 prize. So go ahead and do that, and if you do all those drills, I will give you some extra credit points at the end when I compute the final grade. Right. Anything else you guys can think of? There's a final exam that's May 3rd. I'll tell you more about that next week, but it's not required. We want you to take it, but it's not going to harm you if you do not take it. Okay, so if you want to see how well you did in this course, you can take the final exam, and that's at 11 a.m. It's on Canvas. Okay. Canvas. It's also cumulative, and it will replace a low score. But if you don't do well, you don't do well. It's not gonna harm your final grade. Anything else? Joshua's not here. One day he's not here. It's the day I have his little chemistry set. Oh, he's going to be late? Okay, well, we will give him his chemistry set when he comes. Okay. So let's go ahead and do a practice problem here. Get into the knack, bless you, get into the knack of how to do these problems. Let me turn off the lights. All right, so let's do example 2 together. This is where we left off from last time. So it's asking, what is the standard EMF? So I want to tell you guys that EMF is just a fancy word for voltage, and it stands for electromotive force. But really, it's just a fancy word for volts. Okay, how many volts? Okay. And another word I want you guys to keep in the back of your mind is standard. Okay, so standard is going to mean standard state. Standard EMF, voltage of a galvanic cell. So the galvanic cell actually has two parts. It consists of an anode and a cathode. Kind of like a battery. And this battery, again, which is cathode and anode, is made up of a cadmium electrode. Okay, cadmium electrode. So this we're going to call cadmium solid. In a 1 molar cadmium nitrate solution. All right, so cadmium nitrate, remember all nitrates are soluble. So all nitrates are soluble. Soluble basically means that this cadmium nitrate solution, solute plus solvent, really is nothing more than CD plus 2 and NO3 minus. Okay. That's what we mean by a cadmium nitrate solution. All right, and a chromium electrode, so we'll call that CRS, in a 1 molar chromium nitrate solution. Once again, just like this cadmium nitrate, the chromium nitrate, Cr, is chromium. This chromium nitrate is, here's the formula they gave us. It's going to be CrNO33, but you know, all nitrates are soluble. That's the first thing I kind of drill all the way back in Chem 1. So chromium nitrate really is nothing more than NO3 minus and Cr plus 3. So this is Cr plus 3 aqueous. And this is CD plus 2 aqueous. Okay. All right, so we have here cadmium solid and cadmium plus 2. And then we have chromium solid right here and chromium plus 3. Okay, cadmium plus 2 is in water, chromium plus 3 is in water. All right, so let's, first thing, how we attack this problem. Let's get our little table out. Do you have a copy of this? You want to take this for the exam? You got it? Okay. Yeah, got it. I have lots of these in case if you need one. We have chromium. Let's do cadmium first. We have cadmium and cadmium plus 2. So let's look at that here. Where do we see this? Okay. You guys see it right here? All right, so let's go ahead and write that down along with the voltage. So cadmium plus 2 V minus. Goes to cadmium solid. And what is the voltage with that? Minus 0.040 volts. Okay, hope I'm seeing that straight. Okay. All right, let's do the same thing for chromium. Where's chromium Cr here? Here it is. Everyone see that? Okay. And Cr plus 3 electrons goes to Cr solid. And what's the voltage associated with that? Negative 0.74 volts. So, all of these are reduction reactions. All of these are reduction. In fact, it's called the standard reduction potential. Okay. So, let's say we want to make a battery here. Okay, which one should we flip to make positive so that we get a positive voltage at the end? Absolutely. So we're going to flip the bottom one. Very good. We want a positive voltage. Okay. Bye-bye. So we're going to flip half reaction 2. Come on. We're going to flip half reaction 2. It just wants to do that. It hates us. Autofocus. All right, we'll flip half reaction 2. And so yes, very good, Adriana. Thank you. We'll flip this so that becomes Cr plus 3, chromium plus 3, plus 3 E minus. Okay, now this becomes positive 0.74 volts. Okay, by the way, this also becomes an oxidation anode. Okay, oxidation half reaction. And anode is the site where oxidation happens. Okay, remember, red cat eats an ox. Red cat eats an ox. So anode is where oxidation happens, so we can also call this the anode. We're going to keep this cadmium CD the same as it is, so let's just rewrite this as it is. CD plus 2 aqueous plus 2 E minus goes to CD solid, keeping that as it is. And this is a reduction half reaction, okay? Reduction. It's very important that you don't mix these up. I've seen this a lot. A lot of students will miss. They switch it, right? So don't do that. This is a reduction half reaction. And reduction is, the cathode is where reduction happens. Right, so we're not done yet. We're going to cancel out the free electrons. In order to do that, I have lost 3 electrons here. Let's multiply that by 2. Here I've gained 2 electrons. Let's multiply this by 3. So let me write everything out now. We have 2Cr. Solid goes to 2Cr plus 3 plus 6E minus. Does this stay the same at 0.74 volts? Okay, yes. Okay, this is something that's also can trick you. Okay, it's still at 0.74 volts. And we'll do the same thing for a bottom half reaction. Notice the term here, a half reaction. So 3CD cadmium solid goes to 3CD plus 2 aqueous. Oh no, what am I doing? Three CD plus 2 aqueous plus 6E minus goes to 3CD solid. Okay, that stays the same at 0.40 volts. So let's add these two guys together. We're going to add the anode that lost 6 electrons with the cathode that gained 6 electrons. All right, so canceling out the electrons, 6 electrons here cancels out with 6 electrons there. Our net reaction is going to be 2Cr solid plus 3CD plus 2 aqueous, and that's going to go to 2Cr plus 3 aqueous plus 3CD solid. And the voltage associated with that is going to be positive 0.34 volts. Okay, so we have a successful battery containing the elements chromium and cadmium ion. It's a battery, and the chromium ion gets oxidized to Cr plus 3. The cadmium ion gets reduced to cadmium solid. In fact, I think we have batteries that are made of cadmium, if I'm not mistaken, right? The Energizer battery and all those are made of cadmium. And nickel, I think. So that is the answer, and this is a spontaneous reaction because of the positive voltage. So meaning this reaction is going to move forward. Okay, by the way, how many electrons are transferred in this oxidation reduction reaction? How many? Okay, this is how many electron transfer? Okay, this is a 6 electron transfer reaction. Okay, 6 electrons get transferred. Everyone see that? 6. It's not 3, it's not 2, it's 6. Everyone see that? So, just want to remind everyone this is an 6 electron transfer reaction. 6 electrons are being transferred. And then finally, I also want to mention another thing. Can we put this into the cell notation? What is the cell notation? It's the anode couple. We'll do a salt bridge, cathode couple. Anode couple, cathode couple. That's the order in which these things go in. So the anode, what's the anode? It's going to be right here, Cr solid going to Cr plus 3. So we're going to write Cr solid. We're going to put one line, Cr plus 3, aqueous. Then we'll draw our salt bridge. And then the cathode couple. What's the cathode couple? That's the site where reduction happens. That's the site where electrons are gained. And that's going to be Cd plus 2, aqueous. We're going to draw one line and then Cd solid. So let me box these two here in pink. What I want you guys to be comfortable with is going back and forth between this oxidation reduction reaction and this notation, because these two are essentially the same. So if I give you this, you should be able to get that. And if I give you that, you should be able to get this. So this is how you do these types of problems. Okay, let's just shift gears a little bit here. And don't forget, the positive voltage means, obviously, if you're negative voltage, there's no such thing. There's no such thing as a negative voltage. It's a dead battery. So positive voltage is what we're looking for here, okay, if you want a battery. Okay, very crude battery, but it's a battery. All right, let's sort of fuse all what we've learned in the last couple of chapters together. Which is the equilibrium constant, capital K. Delta G, which tells us whether a reaction is exergonic or endergonic. You must remember that delta G takes input from three things: temperature, enthalpy, delta H, and entropy, S. And then finally, what we're just learning here, E cell. Okay, E cell. I should actually put here delta G naught, okay, because we're kind of standard state. Okay, equilibrium constant, delta G naught, and E cell. Okay, we're going to relate them in standard state conditions. Standard state conditions. So what you see on page 7, the next page here, are a bunch of equations that sort of relate all of these. So this is equilibrium reaction. This is thermodynamics. This is electrochemistry, and in the next page, we have all of these equations that relate one to the other. So I will give you these equations on the exam. It's not something for you to memorize, but it may be good to just look at it and realize that this is electrochemistry. Like I said before, this is electrochemistry. This is equilibrium. Okay, remember equilibrium. Equilibrium, the reaction does not go to 100%. Okay, it settles. It will either settle where there's more products relative to reactants. It will settle where there's more reactants relative to products. It may be 50-50. That's an equilibrium constant of 1. Okay, so the reaction at the end of the day, at the end of the hour, at the end of time, it's just going to settle. It's not 100% forward, and neither is it 100% reactants. Okay, there's some mixture of both reactants and products. So that's K. E cell is electrochemistry. Some of these chemicals can get oxidized. The other one gets reduced, so that's electrochemistry. And then this is pure thermodynamics, where the reaction is going to go from the perspective of energy. So all of these equations relate one to the other. And again, notice here standard state by that not symbol. Standard state, which is, if you're talking about a gas, 1 atmosphere, temperature 25 degrees, and if you're talking about something that's in water in a solution, it's 1 molar. So all of these equations are related to the fact that the reaction conditions were measured at standard state. I want to bring your attention here to F. Okay, F stands for the Faraday Constant. And here's the value for the Faraday constant right here. Faraday, by the way, is the Faraday is the unit, and it is it's what am I trying to say? It's a charge, unit of charge. Okay, or something that measures charge. Okay, an electron is a charged particle, charge -1. So this is a constant. I'll give you all the constants, and the constant is 96,500 coulombs per mole. Okay, this C here is called a coulomb. And coulomb is the base unit for charge, the SI base unit for charge. And 1 coulomb is 1 joules, which is a unit of energy, and voltage, which is a unit of charge as well. So that is the derived unit for a coulomb. Well, what does this mean in terms of testing or in terms of what you need to know for any exam? You just need to know that F is this value, and I'll give you that because I do not make anyone memorize constants. So anytime you see F, you're going to plug in this value here. Okay. And another thing which may be a little bit foreign to you guys is N. And N, as we talked about before, is the number of electrons that get transferred. Okay. N is the number of electrons that get transferred in the oxidation reduction reaction. And so R is your gas constant. We're familiar with this, 8.314 joules over mole Kelvin. I'll give you that on the exam. And T is capital T, large T is temperature, and that has to be in Kelvin. Okay. With all of that, you're able to calculate E of cell, okay, cathode and anode. So, yeah, all right. So all of these equations are sort of interrelated to one another. Once again, thermodynamics, electrochemistry, and equilibrium. Okay, whether the reaction favors products more or favors reactants more. Okay, by the way, if you plug in R here for 8. Let's move back here. If you plug in R here for 8.314, have that value for R, and because this is at standard state, temperature is going to be 298 Kelvin for 25 degrees C. And if you plug in F, which is just a constant 96,500, you plug in all those values here, you're going to get this value, okay, 0.0257. Okay, that is if you put in R, the gas constant, T, 25 degrees or 298 Kelvin, and F, this 96,500. That will give you 0.0257 divided by N, N being the number of electrons transferred. Okay. So there's one form of the equation. There's also a log form. Okay, so a log form. So I'll give you this. I'll probably give you this on the exam and have you put in R and F and all of that stuff. But if you go ahead and plug in those constants, the natural log form is this, or there's a log form, which is that. Okay. All right. I like this table here, so let's go over this table really quickly, and then we have, 3 or 4 more problems to go. All right, so the question I have to ask you guys is, how do you know if a reaction will go to the product side? How will you know whether the reaction will go forward? Okay, that's what we want to move. We want to move forward in chemistry. And if you're a reaction, what can you do so that you can make the reaction move forward? Okay, we're interested in products. So I'll preface this by saying, how will you know a reaction will move towards products? Okay, I will say this. How will you know a reaction will favor products? Okay. Okay, well, there's 3 things. Number 1, the equilibrium constant should be much, much greater than 1. Okay, remember, if you had $1 million, are you moving forward in life or backward in life? You're definitely moving forward if you have $1 million. A lot more conveniences, a lot more things you can get with $1 million. Well, if your equilibrium constant is 1 million, there's no units. No units. If your equilibrium constant is 1 million, yes, that reaction is moving forward. Okay. So that's one criteria that the reaction will move towards the products. Second thing is if the reaction is exergonic, which means that it releases energy. Okay, remember, this delta G naught takes input from temperature T, delta H, and delta S. But it's the final judge, the final arbiter, whether a reaction will move forward. And if that value is negative, the reaction releases energy, releases free energy. This is useful energy that could be harnessed or captured or whatever. Okay. And then the third thing, whether a reaction will favor the products, is whether you have a positive voltage or not. Okay. Obviously, a negative something that gives you a negative voltage is dead. Something that gives you a positive obviously something that gives you a negative voltage is dead. Okay, something that gives you a positive voltage, something viable. Okay. So these are the 3 things sort of shown here that will tell us whether a reaction will favor the products. If it's not favoring the products, well, everything here is the opposite. K will be very small. Delta G will be positive. We call that an endergonic reaction. And you have negative voltage. Negative voltage, not going anywhere. Okay. All right, so those are the three things sort of encapsulated here in this box. And this would be a good multiple choice question. Okay, good multiple choice question for next Wednesday's examination. All right, let's do a couple of more problems here. Winding this up. Sort of. All right, calculate the equilibrium constant. Okay, I hope you're not having nightmares from test 3. Okay, where you did equilibrium constants. But here we're asked to calculate the equilibrium constant for the following reaction at 25 degrees C. Right, so first thing first, let's break this down. I have iron plus 2 going to iron plus, iron solid, excuse me. So let's, okay, let's just do it here. We have iron plus 2 going to iron solid. Let's suggest balance this. How many electrons will balance this reaction? Anyone saying 2? And which side? I'm thinking the left, right? So minus 2 minus 2 plus 2 is 0, and on the product side it's 0. So let's look at our table here. Iron plus 2 E minus, how much? Okay, I see it right here. Everyone see this? Negative 0.44, yeah. By the way, is this reduction or oxidation? Okay, we read it straight out from the table, right? So it is a reduction. Very good. Cathode or anode? Cathode or anode? Red cat eats an ox. Cathode, red cat. All right, so that's our first half reaction. Again, notice the word here, half reaction. And then our second half reaction is Ag going to Ag plus. Ag going to Ag plus. I'm going to avoid the numbers, the superscript, the coefficients for now. You can put them if you want, but I won't put them anyway. So Ag goes to Ag plus. Okay, how many electrons and where to balance this? 1, and we got to put it in the product side. Okay, everyone see that? So here, plus 1 minus 1 is 0, and then we have 0 on the reactant side. Okay, let's look and see where this is at in our table here. Where? I don't see it. Here? Yes, very good. Thank you. Thank you. Okay, 0.8, but you have to flip it, so it's negative 0.8. Very good. Okay, very nicely done. I like that. 0.8, but you have to flip it, okay? And this is a oxidation reaction because we had to flip it. And oxidation occurs where? Cathode or anode? Anode. Okay. All right, how will we cancel out the electrons? To me, I'm going to multiply the bottom half reaction by 2. Okay, multiply the bottom half reaction by 2. Leave the top one alone. Okay, leave the top one alone. So bear with me while I rewrite everything out. Okay, so leaving the top one alone, we have 2E minus plus Fe plus 2 goes to Fe solid. and that's minus 0.44 volts. And here, the bottom half reaction is 2Ag solid going to 2Ag plus 2E minus, and that's minus 0.80 volts. Okay, so once again, here we have the cathode, and here we have the anode. And yeah, let's cancel out those electrons. This is a 2-electron transfer reaction. And our net reaction is going to be Fe plus 2 plus 2Ag solid goes to Fe solid plus 2Ag plus. Well, that's the same thing here. I just had the same net equation, but I got the same equation up here, but the powerful piece of information here that I got is I got the voltage associated with that battery, and that is minus 1.21 volts, minus 0.44 plus a minus 0.80. I should be able to do this on my head, but minus 1.24. Thank you. Okay. All right. That negative voltage. Okay, it means this is a non-spontaneous reaction. It's not going to go. It's a dead battery. That is, you cannot have a battery that will reduce iron plus 2 to iron solid at the same time oxidizing Ag solid to Ag plus. It's not going to happen. Okay, not going to happen. Why? Because of the negative 1.24 volts. All right, the question here, though, is what is the equilibrium constant? So which equation we'll use? Let's go ahead and use this equation. Okay. So, by the way, this is E cell, cathode and anode. So the equation here, and I'll give you this equation on the test. E cell at standard state is RT over NF. Just copying the equation, natural log of K. Okay, we've got to solve for K here to get our equilibrium constant K. Okay. Calculate the equilibrium constant. All right, so we already got E cell minus 1.21 volts equals RT. R here is 8.314 joules divided by mole Kelvin. Say that again? Minus 1.24. Sorry. Thank you. Okay. Okay, so minus 1.24 equals R, and then T is standard state, which is going to be 298 Kelvin. N, how many electrons are being transferred here? Okay, 2 is the correct answer. Okay, so 2 electrons are being transferred. Okay. And then F here is 96,500. And the units of this that I'm going to use is Coulomb per mole. Okay. Now remember, 1 Coulomb is equal to 1 joule over volt. Okay, so it's actually going to be, I'll just change the units here, joule over volt mole. All of that times natural log of K. Do you guys see what I did here? The actual constant that's given to us in the textbook is 96,500 Coulomb per mole. But 1 Coulomb is derived from 1 joule and 1 volt. So I'm just plugging that in here. So here, Faraday's constant is 96,500. 1 coulomb, but coulomb is joule over volt, and then the mole is here. Alright, so some messy math here. By the way, the Kelvin cancels, the mole cancel, the joule and the joule cancel, and this volt and that volt will cancel. This volt and that volt will cancel. Alright, let's do this on our calculator together here. 8.314 times 298 divided by parentheses 2 times 96,500. Okay, that equals to this messy number, which is 0.0128. I'll just add an extra digit here. 4 natural log of K equals 1.24 volts. But the volt and volt cancel. You see, this volt and that volt will cancel. So natural log of K is equal to minus 1.24 divided by 0.01284. So natural log of K is going to equal to, so let's do this here, minus 1.24 divided by 0.01284. That's equals to natural log of K minus 96.573. So we'll take the E of that, the inverse natural log, to get K. And let's see what we get when we do that. So we'll take the inverse natural log of the answer. 1.14 times 10 to the minus 42 is what I'm getting. Okay, is that something you guys got? Okay, very good, thank you. Okay, a very, very, very small number, super small number. The super small number here for equilibrium constant, which is the answer that they're wanting, alongside the negative voltage, should tell you that this reaction is a no-go. Okay, this is not a functioning battery. All right. All right, let's just take a couple of minutes and do this problem here. So before I leave this problem, these two, what I want to mention to you guys is that these two corroborate. This is negative, meaning reaction is not going to go. This is super small, reaction is not going to go. If you have 10 to the minus 42, I mean, that's practically nothing. Okay? All right, let's do this problem here. Calculate delta G naught for the following reaction at 25 degrees C. Here we have Al plus 3 going to Al solid, so let's do that here. So I'll avoid the numbers for now. We'll get them later. Al plus 3 goes to Al solid. Okay, so how many electrons and where to balance this half reaction? 3 on the left side, so that's a reduction. We gain 3 electrons. And what is that here? Anyone see it? Come on, here we go, I got it. It's a race to see who gets first. I can find this. Negative 1.66 volts. Keep it as is. And then we have here Mg solid going to Mg plus. Mg solid going to Mg plus. Okay, how many electrons and where? Mg plus 2. Yeah. Plus 2. Mg plus 2. 2 along the product side. Joshua's right. And let's see where that falls in here. Okay. I got it. Yeah, but what do we need to do with it? We have to flip it. Everyone see that? We have to flip it. So it's going to be positive 2.37 volts. Okay, by the way, this is the cathode that gained 3 electrons. This is the anode that lost 2 electrons. Let's go ahead and multiply the top part by 2 and multiply the bottom half reaction by 3. So doing that, we have 6E minus plus 2Al plus 3 goes to 2Al, and that's minus 1.66 volts. And then here we have 3 mg solid goes to 3 mg plus 2 plus 6E minus, and that is positive 2.37 volts. Alright, the 6 electrons here cancels out with the 6 electrons there. Let's go ahead and write our net reaction, which is just going to be the same as above. But the difference is we have a voltage now, right? So 3 mg solid plus 2Al plus 3 aqueous. And you guys see that's going to go to 2Al solid plus 3 mg plus 2. All right, minus 1.66 plus 2.37. 0.71 volts. Okay. And that is my value for E cell. And we can go ahead and calculate delta G for this reaction. Which equation do you guys want to use? Which one from the triangle we'll take? Top left. Delta G naught is minus NF E cell. Okay, so we'll use that to calculate delta G. How many electrons are transferred in this reaction? 6. This is a 6 electron transfer reaction. All right, we'll finish this up on Friday, and have a good day, everyone. We'll finish this up and see where we are at on Friday. So, want to give this to Joshua. He won the chemistry award. Okay. There's only 2 people that could get selected, so. Well, thank you, Joshua, and I think there should be a certificate that's going to come with this whenever. So thank you again.